As you have probably noticed, um, there is in our class there is a component compute observables and compare to experiments. So last two boxes. So it is basically what we were doing on the last lecture. So here are the subjects that we will present in 3 weeks. So old theories that we covered before were using concept of a function that depends on several electronic positions. And new, simpler theory will use only charge density, but both of them arrive to the total energy. And if both theories will be equally good, they should arrive to the same total energy. If they diverge, it is because of different approximations. So here is a little plan for the next month, how we are going to process this theory. We'll start with definitions, like basically what is density and background theory, which is Thomas Fermi. It is approximate theory, not for molecules, but for simple model. And then we'll go for two theorems, one theorem per lecture. Then we'll set up practical algorithm in the same way as we did for optimization of geometry and for Hartree-Fock theory, and then we will revisit observables. So I understand this is not the best handwriting I can offer, but I promise myself to write it better from year to year. So let's look on the first equation. So suppose we do have orbitals, and we take the orbital with the same index and multiply it by itself. How would you describe what this corresponds to? Lina?
So it's describing the probability density of the particle.
To find particle in the certain
in
position in
certain
the space.
Position in the space.
Yes, absolutely correct. So it is if one multiplies this thing by delta x or delta r, then it will be probability to find the particle in the volume between r and r plus delta r, with understanding that it is like three-dimensional little element, little cube in space. So traditional interpretation of quantum theory, it is that it is probability. At the very first equation, we are updating our consideration, and we will tell that it is not probability, but it is density. In the following, and this statement was inducing objections of in the community for years. So let's imagine that electron is not a wave of probability, but it is like a piece of jelly or gravy or porridge that you just, or like paint that one distributes over some space. So instead of correct definition that there is one electron, but there is a probability for it to be here and there, let's assume that it is a continuous object that is spread over space. And it has a little density to be here and there. It is not assumed to be correct, but if we think in this paradigm, it will be constructive and helpful for the next month. Now, if we integrate, so it is interpreted in the correct way as probability, but now we speak that it is density of the electron, or density distribution. So if one integrates this space or this distribution for a given orbital over, let's say, one can put the letter R3 or V. So basically integrates over all areas of space. Then what is the answer? Boston?
So it'll be 1. Sorry, I've seen it.
That's okay. Why it is 1?
Because if you integrate over all areas of space, you have to have, well, if you're looking at in the probability sense, it has to be somewhere in space. So
okay. So if you speak about 1 electron, and if you look over overall probability, it will be somewhere. Yes.
Yeah.
Good. Okay. Now, suppose that we have so many orbitals. Let me write in 2. Okay, we have number of orbitals equals, and here is there a little ambiguity, but to be correct, one should say 2 homos. 2 number of, like if homo is whatever 32, the number of electrons will be 64, as in our lab. So let's develop such density distribution or probability distribution for all orbitals, for each orbital from 1 to the last one, and maybe place factor 2 in front of each of them because we have 2 electrons per orbital. So if integral of each individual density equals 1, and we add together densities for all orbitals, for all occupied orbitals, then what will be the integral of such total density over the whole space? K. Please try to tell what you see.
I don't get it.
Okay, so at which point you feel discomfort? So first equation, is it okay?
Yeah, it's a density distribution function.
Okay, second, is it okay?
No.
No?
No.
Okay, so each good wave function must be normalized, right? So by normalization, if we integrate wave function by itself, if it is the same number, dr, it will be equal 1.
Okay, it's 1 because of orthogonality, right?
Exactly, 1 because of orthogonality. Make sense?
Yeah, makes sense.
And we just redefine this product as rho sub I.
Okay.
Okay. Now we have rho sub 1, rho sub 2, rho sub and the last one rho sub homo.
Okay.
What will be integral for each if you take integral of this densities? If you integrate each of this rho, what will be the result of individual integration for each of them?
So we need to sum up the all density.
Yes. So
then we need after that we need to integrate that one.
Yes, but if we integrate, we can integrate them individually, right?
Okay, individually, then we will get 1 because of orthogonality.
And if we do it for each orbital, then we will need to add together 1 plus 1 plus 1. so many times as many orbitals we have in our model, right?
Yes.
So what will be the result?
You show 2 HOMO?
Yes, and which will be equal to the total number of electrons, right?
Okay.
So now we have indirect definition of the density. So or main property of the density. So it is such function, total density. By integrating this function, one will obtain total number of electrons in the model. Make sense?
Yeah.
And density is typical is in chemistry community. It is denoted with letter rho. In physics community is often referred to by letter n lowercase. Just if you read paper, you can say whether paper is written by a person employed in physics department or chemistry department by notations. And total number of electrons is often in capital. So the community often uses rectangular brackets as a symbol of this integration. And this rectangular brackets means that total number of electrons is a functional of the density. So let me try someone else. Lola, would you share your expectations? What does the word functional mean? Just based on what we discussed now.
The dependence.
Dependence, yes. But what is the difference between function and functional? Why we use this additional 2 letters AL at the end?
I don't know.
But just looking on the previous line, give an example how the density is converted into number of electrons. By which operation?
Integral.
Yes, integral. So we start with a function and we get a number at the output, right?
Yeah.
Okay, and in the regular calculus, when we use concept of a function, we typically, when we, for example, analyze experimental data and use Excel tables, we typically have x and y. We have argument and a function. And for each value of the argument, which is number, we have corresponding value of a function. So for x1, we get y1. For x2, we get y2. Correct?
Yeah.
Okay. And here we see a little difference. So before for function, we get from one number, we get another number. And here we start already with a function, and as a result, we get a number. So when we convert a number to a number, I'm not good in writing, then it is a function. And when we convert function into a number. How do we call it? What? Just
Functional.
yes, exactly. Thank you. Thank you so much. So we have a definition of a function. When we have a distribution, a function, and convert it into a number. And the simplest example is that density of electrons is converted into a number of electrons. Okay, very good. Thank you. So I am going to follow the following 8 steps, and it will be a long derivation. I have no doubts that we all will follow and understand it, but just in case, let me quickly jump to the last slide so that we are not wandering in the dark, but we know what is the goal. So at the very end, I want to obtain this equation. So I want to obtain total energy as a functional of the density. And the answer that it will be integral of total density in the certain power over the whole space. So it will be not for a molecule. It will be for a specific molecule, for a universe that has no atoms, only electrons. But it is an important intellectual step towards developing practical density functional theory for our materials, computational modeling of materials. So, and I think we have about half an hour or about 30 slides, so a slide per minute in my pace. So all efforts that I will commit will be directed towards obtaining this equation. And philosophy is that at least in some simple examples, one can avoid solving multi-electron Schrödinger equation. One can avoid computing Coulomb exchange. One can just integrate the density, which looks like a magic. It is a dramatic speed up, if it is possible at all. Okay. So and here is the plan. So the model that we will consider today will be an artificial universe, a universe which does not have positive ions, it has only negative electrons. And there is an additional approximation that if you are a serious scientist, you will be laughing at. So it will be a universe where electrons do not interact with each other. But we need to make this model just as a little toy step to develop approaches. And later on, we will bring interaction back on next lecture. So what do I need from my previous life or from background science and in quantum theory? I need high school geometry in the sense of how to find a volume of a sphere. So do not tell it to me right now, but start thinking about it and maybe write on your scratch paper. So volume of a sphere. If you remember this equation, you will feel very comfortable today. Another thing, from the basic level quantum theory, we will need concept of particle in the box. I will quickly revisit it. So if you have this concept in your background, you will feel just relaxed and very comfortable. If you don't, I'll remind what it is and we'll go over. And the rest will be just math and connecting these concepts. So what is the plan? What is the strategy? about 2,000 years ago, one of the strongest countries in the world was Roman Empire. And when they developed their approach, how to like be in strength, it doesn't mean that we should confirm and agree. But one of the principles of the Roman Empire was divide and conquer. We shouldn't support it in diplomacy and interaction between states, but if we take this principle as a approach to analyze different pieces of knowledge, then is nothing wrong with it, because small pieces are easier to understand than bigger pieces. So let's apply divide and conquer approach to this universe that contains of non-interacting electrons. And this principle is symbolized in these little boxes. So I will try to chop the universe on boxes. So supposing that or little cages, like if one goes to supermarket to buy eggs, typically it writes cage-free chicken were source of this eggs. So now we go back. We have universe with cages. So equal boxes, cubes, and we will assume that electrons, since they do not interact, since they move as they want, statistically they will distribute equivalently over each of these boxes. And now I'm going to focus on individual box and explore properties of the electrons inside the box, and then extrapolate property of one box onto the overall universe. So if the size of the box is L in each direction, lowercase l, and total number of electrons, we use letter n for total number of electrons, but the number of electrons in one box will be dn, then the ratio number of electrons per volume of a box, which is L cube, will be density of electrons in our universe. So this one is like in middle school or beginning of high school physics, Archimedes law, right? Density of, before we had density of matter, now we speak about density of electrons. And instead of mass, we tell just number. So then there will be several steps. Oh, I had forgotten. There is one more concept that we will need for the background information. We need the Fermi distribution, which is the basically Fermi distribution is the same as Aufbau principle. It follows from Pauli exclusion principle that one uses that no electron can use the same state, and if you have several states, several orbitals, they are occupied one electron per state. Okay, so basically three input things: volume of sphere, particle in the box, and Fermi distribution. Good. So, and I'm not going to waste time on this plan. It will be reproduced on the side box, and I will highlight what we cover. At the very last step, we will add together energies of individual cube. So we introduce that all electrons in one cube have energies with symbol dE, and then we perform summation and tell that it will be total energy. Okay, start, set, go. Density, particle in the box. Let me friendly challenge some of you. Steven, would you like to tell some of your impressions about particle in the box?
I'm trying to think of something worthwhile to say.
Basically, with my ugly hand scratching, I have all information here, and I just need help in verbalizing it.
Oh. So, well, what's most interesting to me about it is sort of the similarities to musical harmonics.
Uh-huh.
That if you take a pipe of a certain length, it will resonate at a frequency, and then if you put a cap on one end, that will double the frequency. Yes. It's not really related, but it's just
it is related, but it will change the frequency. I wouldn't say double. The law is more complicated, and it is exactly the point that I want us to cover before we go forward. So, would you please tell what I'm drawing right now and how it is related to your concept of doubling frequency in the guitar string?
There would be quantized energy levels.
Okay, okay. And can you navigate which equation in this page corresponds to values of these energies?
So the bottom one, the H2 over ml squared r squared, would be the general form.
Let's think over once again. So, and I will recapitalize in a second, but Steven, you're moving in the right direction. So here we do have indices. So you said absolutely correctly, there are quantized energy levels. So there is energy level for quantum states n equals 1, for n equals 2, for n equals 3, and so forth. So we need an equation that does have this nx as parameter. So because there will be several energies, we need an equation that depends on n sub x. So let's try once again.
Right now, it's the one-dimensional formula.
Yes, exactly. So it is dependence of the energy on this nx parameter. And it will be nx squared. So it is not linear. With going higher up with harmonics, it will be not just linear in nx as for your guitar string, but it will be n squared. Thank you much. Everything is great, moving in the right direction. And I apologize for stopping and discussing, but maybe we will get better to the end so that we do not lose anyone in transit. Sarah, would you please share your impression of what we discussed right now?
We were talking about the quantum states and the related energies for the electrons. I think, and the figure in the left hand shows the each energy correspond to each quantum state. For example, quantum state number 1, number 2, or 3.
Excellent, excellent. Thank you so much. I cannot say better. Thank you. So the starting point for particle in the box that one assumes that the electron is allowed to exist only in the range from 0 to L. So there is a potential energy which is infinite, it is 0 inside the box, and it goes up, 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 and then infinity high, infinity outside of the box. So outside there is no probability for it to exist, and inside the electron can exist in several quantum states. Yeah, on the language of our course, in orbitals, and each orbital has its eigenenergy. And for this simple model, we do not need computers, we don't need computation. The energy for each state is known. And I'll skip the derivation, but it is quite simple. It is one of the few problems that can be derived. So basically, energy of each of these orbitals is quantum number squared, and then there are some additional constants like Planck constant, mass of electron, and size of the box. The smaller the box, the bigger offset of energy. The larger the box, the smaller offset of energy. So please give me a sign if we are good on this. If anyone disagrees, let me know.
Okay.
So I do not see anyone disagreeing. Okay, now our space is three-dimensional and our artificial universe is three-dimensional. If our box is not one-dimensional but three-dimensional, then this equation will have three independent quantum numbers corresponding to motion in x, y, and z, and then the previous equation will be updated, so it will be square of each of these quantum numbers. Okay? So energies will have three indices, and depending on the values of this index, we know the energy of the state. Now, the equation that Stephen pointed out first. Whom I didn't ask? Oh, I will talk myself. Otherwise, I will not have right to receive salary from university if I do not speak. So, the three independent variables squared added together. Do you have any impressions in the mathematical part of your brain? What does three variables squared together symbolize? Just think, or just glance through the slide. It's already written here. Boston? Do not hesitate, just share impressions. Like in high school, when we had three coordinates, x, y, and z.
I'm muted again. A vector squared.
It is a, okay, it's length of a vector, but if we write an equation that x squared plus y squared plus z squared equals some constant, for example, r squared. Does it correspond to any geometrical figure?
Triangle.
Sphere.
Yes,
Yeah.
Sarah, you
Yeah.
won. You won. Boston, sorry. Boston, if it will be x plus y plus z, it will be like a plane. But if it is squared, it is a sphere. Correct. Yeah. Congratulations, Sarah. So it will be a sphere. I'm not good. I can only show an example of here. Okay, a sphere. So, and let's do an intellectual step forward. In high school, we were thinking about spheres in the realistic Cartesian space. Now let's think about spheres in the space of indices, in the space of quantum numbers. So we have space where we have nx and y and z as independent variable, and we think that it is our space. So we consider the not actual space, but just space filled with the values of quantum numbers. And let's put our brain into the space and try to draw a sphere there. Okay? Sphere. And in this sphere, our next intellectual stops will be to focus on all states that have energies between 0 and the radius in this artificial space, or in the thin layer near the radius. And I will illustrate it. So here I am drawing an example for, instead of sphere, I do a circle, and from 3-dimensional, I go back to 2-dimensional, because otherwise my drawing will be super pathetic. So this is an example of this artificial space of quantum numbers. So you have quantum number nx and quantum number ny, and they have values 1, 2, 3, and so forth, and here 1, 2, 3, and so forth, right? So quantum numbers are discrete. So this space is not continuous, it's just set of points. Now, if we declare nx squared plus ny squared equals r squared, it will define a circle of radius r. Okay, so I'm confident that Sarah agrees with it for sure. And if we can also consider as another circle of a little bit bigger radius, r plus delta r. Now, I formulate a problem for myself. If I know the radius, can I count number of these dots inside the sphere? Of course, I can go in a simple way. I can manually draw this border, this circle, and count 1, 2, 3, 4, 5. Like in this example, it will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. But I want to be more mathematical and give it as a function. So if I know r, I need immediately to know the number of points inside. So if these numbers nx and ny will be really great, really big, not like 1, 2, 3, but like million or like 5 million, then it is as good as continuous number. And then we can just say that amount of points inside this circle is proportional to the area of this figure, right? Okay, area of this figure. And of course, there could be, if you speak about circle, it is defined everywhere on the whole plane. But since quantum numbers have only positive values, we take 1/4 of the circle. The correct word would be quadrant. So we take only for positive nx and ny. So how do we find area of the blue space? Kea, would you please help us?
Area of the blue line.
Not line, the area, the one. Like what is the area of a circle with a radius r?
Pi r square.
Correct.
Or circle. But
Yeah,
for this one is
pi r squared. Correct.
For circle, yes.
And here we put one fourth, right?
Yeah.
Thank you. Thank you so much. Correct. So if we need a number of states in this little layer, then we need just to differentiate this area, the equation for area. And if you want to extrapolate this equation for three-dimensional case, which I'm just not able to draw, then the amount of states will be, so here is what we should remember from our high school. 4/3 PRQ, right?
Yes.
Okay. And if I need to find amount of states inside this black, inside this area, then it will be a derivative of the volume, right? In respect to the radius. So it will be, if you take derivative of r cubed, we have 3 r squared. Here are 4/3, and then we have dr for the thickness of the layer. Okay, would you approve this? Or should I speak more about it?
Yes, it's okay.
Okay. Please give me signs if it is okay, or should I speak a little bit more about it? Okay, so no one requested additional. So this 3r squared is just the derivative of r cubed, right? So by now we do know the number of states that give radius in this space, give certain radius in this space. So can we combine, can we return from the parameter of this radius, which is not very well defined, to the parameter of energy? Can we speak about energy instead of this radius? So when we originally introduced the equation for energy of a state in three-dimensional box, and it is basically the equation that Stephen pointed the interest to. So we have this radius squared, which includes quantum numbers and x and y and z, then product of constants, including size of the box, and then it gives energy, right? Now, let's inverse this equation. Let's invert this equation and express radius in which is not well defined in terms of the energy, which is really well understood what it is. So if the energy as function of radius is radius squared, then the radius as function of energy is square root of energy, right? Square root of energy, and then some square root of constants. Mass, length, constant. So I'm going to combine this recent finding with our equation for number of states inside a certain radius. So I'm just plugging this R into this equation. And laziness is not good for everyone, but good for me. I think everyone thinks this way. So let's save time and forget about constant and this mass, length, Planck constant. Let's just get the main thing. So if you have a square root in the power 3, then it will be energy into power 2/3, right? So, and this is number of states with energy epsilon. So we know if the energy is provided, we know how many states or particles for three-dimensional box will be equal or less than this energy. Okay. Now, let me count how many states will be in the thin layer on the surface of this sphere. So instead of derivative over radius, I can do derivative over energy, right? And derivative of the e to the power 3 halves. After taking derivative, we will have energy to power 1/2, right? By the way, this one was number of states. And derivative of number of states in respect to energy is density of state. So it relates to the practical things that we do in the class. So we do have number of states on a sphere, on a surface of a sphere, right? And this density number of states on the surface or density of states is square root of energy. So for three-dimensional object. Good. Now, I'm trying to look on all possible energies starting from the zero. So I'm imagining like a core part of the sphere, then a little bigger sphere, a little bigger sphere, a little bigger sphere, and expanding. And then for each of these shells, I know how many states are there. Now, as I go to bigger and bigger energy, I ask myself whether this state of a certain energy will be populated, will be occupied or not. Because we know our Bohr principle, because we know that there is a certain number of electrons in the system. And we know that electrons tend to take only the lowest state. I know that there will be a border. Up to certain range, they will be occupied, and then it will be empty state, unoccupied. So generally, this is described by Fermi distribution function, and this I hate this equation because it is too complicated for me. But if I need to draw it and imagine what does it mean, I can do it stepwise. So first, I can draw this exponential to the power of energy, and it is just increasing function. Then I add 1, and it is just shifting everything up, right? And then dividing 1 over this stuff. Then if we have argument equals to minus infinity, it will be 1 divided by 1 will be 1. If I go to plus infinity, it will be 1 divided by infinity, and it will be 0. And in the middle, it will be transition, right? If the temperature parameter tends to 0, then instead of this continuous function, it will be just step function. So Fermi energy, 1 means states are occupied, 0 means states are unoccupied. Energy Fermi, it is corresponding to HOMO in our molecules, right? So all orbitals before and equal HOMO are occupied, everything after are unoccupied. And it is in chemistry language. In physics language, all electrons obey Fermi distribution, which at 0 temperature is just a step function. Now, I do have density of states, but only states up to Fermi energy are occupied. Everything after are empty, and I can forget about them. So if I do any considerations, I can stop at Fermi energy at home. Okay. So here is the question. What is the energy of all electrons inside one box? So I should consider spheres starting from 0 radius, 0 energy, bigger, 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 and stop at that sphere that is not occupied, right? So if I speak at the language of distributions, I need to multiply this density of states, DOS, or D by capital over energy, which we know it's square root of energy. Then times Fermi distribution, which is either 0 or 1, depending on energy, times energy, right? Standard way. I multiply distribution times value times observable. And if I integrate, it will be total energy. So here is a little mathematical exercise. I do not like this Fermi distribution, and maybe you do not like it as well. So instead of looking at this complicated equation, instead of integrating from 0 to Fermi energy, Fermi, I am going to integrate only until Fermi energy, right? Because after it will give 0 contributions, and then I need just to multiply this density of states times energy. So basically, my mathematical problem is energy times square root of energy integrate over energy. Make sense? So we basically integrate e to the power 3/2 over energy. And integration lifts up the power by 1. So instead of 3/2, after integration, we have 5/2. And at 0, we will have 0, and at upper limit, we will have Fermi energy. So here is the consideration that energy of all states inside the box will be equal Fermi energy to the power 5/2. Okay, and I'll speed up. I'll be finished quite quick. We covered main stuff. Now I want to repeat the same consideration for number of electrons inside the box, and you will see why I need it in shortly. So if I need just number of electrons inside the box, I do not have energy here. I just multiply density of states times Fermi distribution over energy, and I do the same trick. I remove Fermi distribution and just perform integration until the certain limit, right? So, and which will give number of electrons. So I integrate this density of states, which is energy to the power 1/2, from 0 to Fermi energy. Integration lifts up power from by 1, so to 3/2, and we explore it at 0 at lower and upper limits. At 0 it will be 0, at upper limits Fermi energy power 3/2. Now we do have energy as total energy of all electrons as function of Fermi energy, and we have number of electrons as function of Fermi energy. But our original goal was to express everything as function of number of electrons or density. So I want to invert this dependence and express Fermi energy as function of number of electrons. So number of electrons inside the box is Fermi energy to the power 3 halves. And if I invert this dependence, then the number of then the Fermi energy will be number of electrons into the power 2/3, right? So the Fermi energy is number of electrons in power 2/3. And then I want to plug it into expression for all electrons inside. So I take number of electrons to power 2/3 in power 2 halves. And then 2 and 2 cancel, and we have, as a result, we will have the delta E equals number of electrons to the power 5/3, right? Because 2 has cancelled. We are almost arrived. It's just few seconds left. So we have energy as function of number of electrons inside the box. So here is the here is the little trick. If we have delta n, which is red here, and we multiply and divide it by volume, then in the circle here we will have density. So you have density multiplied by volume. So if you know function of number, we also have function of density. So we have submit the volume inside this 5/3 equation, and as a price we will have volume in the 5/3 outside of this bracket. But since we are arranging this theory to our comfort, we can just insert this volume into power 5/3 into constant. Just redefine the constant that it will include the size of the box. It is not an integration variable. And if you do this trick, then it will be a new constant here, and density of electrons to the power 5/3 outside as an only important factor. So in each box, energy of all electrons will be density of electrons to the power 5/3. And the only thing left is to make a summation over all boxes. So we take make summation of this 5/3 over all boxes in space. And if the boxes are really small, we replace summation by integration. So constants that include mass of electrons, size of the box, Planck constant, are all inserted in this Fermi, C sub F Fermi constant, which let Fermi compute it. It's not our task for today. But the main answer is by performing three-dimensional integration of the density to the power of 5/3, we are arriving to the total energy of all electrons in the universe. And this is very unpractical because this universe doesn't have ions. But with few additional efforts, we will redo such thing for the actual work with molecules and materials. If we have total energy depending as functional on the density only, it is typically called LDA, local density approximation, because we integrate only density. In practical examples, typically one also integrates derivative of density, and then or gradient of density. And majority of functionals are qualified as generalized gradient approximation. And you'll see these abbreviations in the future. So thank you for investing additional time. We are done. Everyone is welcome to disconnect, and I'll stay here to answer questions.
Thanks, Dr. Killen.
Thank you.
Thank you.
Yeah, have a nice break, everyone. Bye.
Oh, nice. Have a nice break, everyone.
Bye.
Thank you. Have a nice day. Goodbye.
Goodbye, sir.